Hello, everybody, and welcome to today's webinar presentation, Advantages of Connectivity, Aware Over-the-Air Updates with LTE-M, brought to you by Aeris. I would like to introduce you to our presenters. Drew Johnson is an engineering leader and technologist with more than 25 years of experience at both large and small companies. Drew started his career at Compaq Computer, working on the first generations of mobile computing devices. Prior to Aeris, he was Director of Engineering at Austin mobile startup Solomio and VP of Engineering at mobile and messaging software company OpenWave. He holds a master's degree in artificial intelligence from the University of Illinois. Secondly, our second presenter is Naren Sharma. Narendra is a seasoned software architect with more than 19 years of experience. Narendra started his career at Persistent Systems, where he worked on architecture and development of large-scale software platforms for telcos in the area of messaging. At Aeris, he is responsible for driving the architecture of current and next-gen mobility platform. He also leads the Aeris Labs, a group that tracks and experiments with emerging technologies relevant to Aeris. And with that, I would like to hand over the presentation to the two of you.
Okay, welcome to the webinar, everyone. Thank you for joining. Just a little bit of background on Aeris in case you're not familiar with us. Aeris, we really provide two products to the market related to the Internet of Things. One is that we provide connectivity for the Internet of Things via our Fusion IoT network, which is based on our IoT optimized cellular network. And the second product offering is our Aeris Mobility Suite. That is a solution platform that can provide you with components for your Internet of Moving Things solutions. And really what's important in both of these areas is that some of the largest companies in the world have selected Aeris for their IoT connectivity. Some of the largest OEM automakers in the world have selected Aeris for our Aeris Mobility Suite. So we're really actually very lucky and fortunate to have such really large, great customers. As you can see there, we have locations all over the world, no matter where you are in the world. Turns out that most IoT deployments are global deployments. No matter where you are in the world, we can help you. And from a people perspective, we have around 300 people. More than 60% of our people are in engineering and operations. And really, what that means to you is that we're a technology company. A lot of those folks are software engineers. We are like many of our customers, being more of an engineering company rather than just operating a network or something like that. Then a few more numbers that tell you a little bit more about Aeris. We have operational connectivity reach in 190 countries. Again, that just goes to pretty much no matter where you're deploying your IoT device, we can provide connectivity. We have 14 million plus devices on our network. That actually puts us in the top 15 network operators with devices under management. And all that and those abilities result in our systems actually handling around 1 billion messages per day. So again, we're doing this. We've been doing this for a long time, doing this at scale for really large companies. Okay. Then today, I just want to make sure that we're aligned around the agenda for today. Again, as the moderator mentioned, today is focused on connectivity-aware OTA. And what we're going to be covering is first, making sure that there's clarity around OTA and the categories of OTA. OTA is a term that gets used really broadly, and we want to make sure that there's clarity about what type of OTA that we're talking about today. Generally, that's application OTA, and then we're going to talk specifically about some of the application OTA use cases. We're also going to be covering LTE-M. This is really focused around OTA over LTE-M. We're going to be talking about the advantages and trade-offs of LTE-M. And then Specifically, we're going to help you understand how OTA interacts with LTE-M and how there could be potential issues. And to further help you understand those potential issues, we'll actually cover a particular case study as well as lab-based empirical data and help you understand really what's going on in those interactions of OTA relative to LTE-M. Finally, we'll come back with a summary and recommendations. And as you might have guessed, the recommendation is around leveraging aerospace connectivity-aware OTA. Okay. So a little bit more about the OTA categories. And again, as what we hear a lot is the term OTA get used in a lot of different contexts. And so it's really important that you actually use the next level descriptor when you talk about OTA. Number one is application or operating system OTA. That again is the primary topic for today. That's about changing more or less all or part of the application or OS of your IoT device. Then there's also related to the behavior of the application configuration OTA. And what's important to understand about configuration OTA, the good thing is that it can be a much smaller amount of OTA data. The challenge is that you would have had to have pre-thought about what behavior you wanted to change via that configuration. So that makes it a powerful capability, but also somewhat limited based on what you've thought about ahead of time relative to what you can change. Another common category is radio module OTA. And this can definitely be important, particularly as new access technologies roll out. There might be kind of minor modifications and interpretations of the specification. We saw that in the field for one of our customers last year, where it was really important that they have this capability to update the radio module firmware. And then a third major category is around the SIM and the subscription, which really fundamentally tells your device which network operator to connect to and provides the authentication and authorization information for getting connected. And there's really two types of OTA related to the SIM. One is, we just call it SIM OTA, or the subscription OTA of whatever is the current subscription that your device is using. And that is a very, very powerful capability because it actually helps your device determine what towers it's able to connect to. And that it could almost deserve its own webinar. We could talk about that. That's one of the areas that is differentiated about Aeris and the ability that we are able to help our customers with that area. Second category that many of you probably hear about is RSP, remote SIM provisioning, OTA, or subscription management, maybe you hear about. And that is about downloading and flipping to a totally different subscription, which would give you a different home network for connecting. So again, today we're going to be talking about the very first category on this page, application operating system, OTA. Okay, and then if we go and talk about the OTA use cases related to application OTA, fundamentally, what we see is there were kind of early first generation IoT devices that got deployed without OTA capabilities, and OTA capability is, you can think of it no longer as being optional, it's really required. And these are the categories and the reasons for why we see OTA updates happening. Number one, of course, is bugs. Pretty much everything that gets delivered has some level of bugs out there. I remember early in my career, being in that situation where a bug is found in the firmware and you'd actually have to stop the factory because we didn't have OTA capabilities at that time. Second is security, and we all know that security now is an arms race. There's no, it doesn't matter how much testing that you do ahead of time related to security, you are likely to run into situations where you need to do an OTA update because of security. Regulations. Regulations are constantly changing, and those regulations might have to do with privacy or frequency of how often that the device is able to or needs to connect to provide its capabilities. And then lastly is features. And oftentimes in today's world, devices and IoT solutions are not static solutions, or they need not to be static solutions. They need to be able to evolve over time. So you need an ability to do OTA updates to roll out new features. And then it's important to think about OTA relative to locations. And there's really two primary categories of locations to think about. One is a factory or distribution center, and the key there is that you've got a bunch of devices together, and they may or may not be on battery power. You oftentimes in that situation, you have a better opportunity to have them be connected, but in some situations, you're still constrained by them being on battery power. And then the other main category there is the field. So generally, the devices are not all together, but they certainly could be clustered around certain towers and certain geographies. Generally, they would be on battery power if you're taking advantages of the powers of or the advantages of LTE-M. And the other piece of information to consider there is whether the device is mobile or fixed. That might determine how you think about how to manage OTA relative to those devices in the field. So just a little bit about LTE-M key advantages and trade-offs. If you're on this webinar, I assume that means you might be thinking about deploying LTE-M, and we have a large number of customers who are really interested in LTE-M because it's a great offering for many IoT use cases. And fundamentally, customers are thinking about LTE-M or moving to LTE-M for these two reasons. Number one is radio module costs less. And the radio module costs less because of some constraints and reduced complexity in the radio module. So it's generally half duplex instead of full duplex. It's constrained to a smaller band and has a single antenna. So it doesn't have all the complexity that higher category LTE radio modules have. And the second main advantage of LTE-M is battery lasts longer. And the battery lasts longer comes from leveraging the power savings mode of LTE-M and also the extended discontinuous reception of LTE-M. And both of those, fundamentally, you get those advantages when you're mostly not connected for large periods of time. So that's really how you need to use the LTE-M radio module in order to get those benefits. So then if we look at those benefits related to the potential impacts on OTA, let's start with battery. So if you have a device that is trying to leverage the long battery life of LTE-M, and then you have a long-running OTA that is consuming energy during that long-running OTA, that can negate the advantage of the battery savings that you're getting. And that, of course, is most acute in the field where the battery matters the most. If you're doing that in a factory or distribution center, at least you have an opportunity potentially to replace the battery or charge the battery in some way. But even in the factory or distribution center, it actually ties up resources like power supplies and impacts throughput of your factory or distribution center. And then the second way that OTAs could have an impact on your LTE-M program is, in a way, loss of service. So, we talked about how LTE-M is half duplex. You have a long-running OTA that is consuming that half duplex, and now you could be losing the actual value of whatever capability your OTA device is trying to deliver, the actual feature that it's delivering. And this, of course, would be most acute in the field where the internet service matters the most. All right, and to explain a little bit more about how we have seen this manifest in the real world, we have this asset tracker OTA case study. This was an asset tracker. It's LTE-M based. It's battery based, so battery power actually matters. You can see some stats there. Modem is U-Blocks, which is a great modem. Processor, OTA is about 150K KB, including the real-time operating system. So these are probably relatively common types of statistics for this kind of solution. The network in this case, tier 1 network, but they have deployed limited physical resource blocks. And if you think about it, all of the networks so far have deployed limited resource blocks. It's what makes sense ahead of where the market is. And in general, the network operators are going to be deploying those resource blocks relative to the LTE-M standard uses, not optimized for the OTA use cases. So I think we can assume that as the population of LTE-M devices grows, there will always be, a level of constraint on the PRBs. And then the OTA requirements in this situation, basically the device is moving quickly to market, and it's very common. The application features and bug fixes are lagging the manufacturing. So they needed to update every device at the distribution center, and then as devices started rolling out into the field and understanding additional edge cases and new features, they needed to be able to also perform those remote updates in the field. And fundamentally, the challenge that they had relative to OTA was the time to complete the OTA, particularly in this case, in the distribution center, because they had to update every single device in the distribution center. Now, in this case, they deployed a couple of different workarounds. One was to actually just reduce the number of simultaneous OTAs. They started with doing 50 in parallel and actually had to go all the way down to performing 2 OTAs in parallel. So you can imagine what that did to kind of overall the expectation of throughput in the factory. And then they split the OTA into parts. That's a good strategy of differential OTA or piecewise OTA. And then worst case, in some cases, they actually had to put the devices on a truck and drive them a mile away to get access to a different tower. So these are the kinds of real-world situations that we've seen customers run into. And now to share a little bit more of us diving into that situation and understanding it better based on some lab testing, we've got Naren to cover more details.
Okay, I want to switch mode and go to the conference page. I'll basically use the conference page to share the details of the experiment. Okay, so thank you, Drew. I think before I share the details of the results, I think one thing is like the key motivation, right? If you look at the case study that Drew described, I think that basically was the key motivation is whether we basically, whether a trial and error based approach that the customer took in this case is the way to basically manage OTA, or could there be a more smart and intelligent way wherein Aeris as a connectivity service provider with a lot of experience in connectivity can basically help provide the intelligence so that the OTA services could be more smarter and can benefit on the key potential challenges or issues that you described with respect to the battery saving with respect to be able to complete OTA downloads quickly. So with that, with that motivation, we went out and did this experiment. And what I'll specifically cover in this in the detail is I'll walk over the test setup, what kind of test setup that we used, both of course the hardware and the software. I'll talk about what kind of tests we did actually, how we executed this test, and then look at the results in detail. And we basically looked at multiple parameters, and I'll basically share details, of a concise summary of each of those results. And finally, we'll conclude, what conclusions we draw from this lab experiment, and also the real field experience that we gained from the case study that Drew just described. So to start with the test setup, so the hardware basically consisted of, we had 8 Raspberry Pis, and they're all running Raspbian OS. They're all plugged to power source. I think the picture basically is explaining what I'm just describing here. And we used the modems from Multitech. These are ESP-LT Cat-M modems, and they're all using Telit ME910C1 module. And these modems were all using the Aeris Fusion IoT SIM and Aeris connectivity. You can definitely learn about the connectivity and the SIM from our website, more details if you're interested. And the next and they're basically all located in the same location, on the same desk, as you can see in the picture. The second is on the software side. On the software side, there are 4 components. One is the OTA content server, or download client, and the scripts to capture the data, to record the data it will analyze, and finally the scripts to analyze. So on the OTA content server, we had a simple Nginx standard web server, which is running on a virtual machine in a Google Cloud platform, had a public IP, and that was as simple as it could get. And on the server, we're basically hosting it on port 80 standard HTTP. It was not running on TLS, just to basically minimize the resource usage both on the client and the server for this particular test. On the download client side, we wrote a small Node.js application client running on Raspberry Pi, and this client was written to download the content. We picked up a 200 KB size image, which was very close to the 150 KB that our customer used. And we basically had this client download the content in chunks of 10 KB. And this is also standard practice, followed by various, all the customers, to this basic constraint by the memory that is available to the application on those constrained devices. And I said, we used HTTP only. And to capture the data for this test, we wrote a set of shell scripts, and we captured data which basically, essentially was logs generated by the client. We also captured the RF stats available using AT commands provided by the modem in this case. And we also captured the TCP dump trace for all the tests to analyze, how the actual, performance at the traffic level is, transport level is. And finally, for data analysis, we basically wrote some Python scripts. Essentially, the objective was just to plot various charts so that we can look at the macro trend and easily identify the differences between various tests. So this was basically the setup, hardware and software setup. Now moving on to the execution. So execution, we basically did 2 types of runs. The first one was a concurrent run, and the second was staggered run. Now in concurrent run, we basically had all these 8 devices. We set up them so that they would basically download the same content from the OTA server at the same time. And we picked up 2 days. We picked up Friday and Saturday, one office day, one non-office day, and we'll see the details, why is that. And we basically had these downloads happen every 2 hours. So every 2 hours, all 8 devices will go and attempt and download the content. And for the staggered run, it was almost same. The difference is we had the devices download at non-overlapping times. And here we picked up the days Sunday and Monday, just wanted to run them in quick succession, not wait for another weekend. And again, the characteristic is pick up one office, non-office day, other is office day. And so we basically ran this for 2 days, so every 2 hours. So we basically had 24 instances of each type. And that basically gave you 24 sets of data points for each of these. So that's, I think, a good data set for us to analyze here. And just to provide more details, what each instance of the run involved, it basically involved, bringing down the Wi-Fi interface to make sure it's not basically using those interfaces, bringing the clean cellular interface every time, start the various, scripts to basically capture statistics and other things in the background. And finally, at the end of the test, we would basically bring down the cellular interface, bring Wi-Fi interface, and reboot the Pi so that we basically have a clean slate for the next set. And after every test, we could basically just download the results. I think one thing worth noting is that even if basically we had this clean setup on each and every test, we still had 10% of failures due to PPP connection issues, cellular connection issues, and I think we're still working on isolating each of those because there are various reasons why they could fail. Now, with this, now we have the context of the setup and execution. Now let's move on to the results. So I said, we captured a lot of statistics, and I'm going to present one by one. And in the table, you can basically see on the left-hand side is the concurrent run results, and on the right-hand side, staggered run results. The first one, the matrix that we looked at was per chunk download latency. And here the lower number is better. And this measurement was the time, the end-to-end time. It was measured on the client, the time the client took to download one chunk of 10 KB. Okay. And as you can see on the left-hand side in the staggered run, the scatter graph, you can see basically, the download latencies basically are highly scattered. The standard deviation basically in case of concurrent run was 17% higher. Okay. Whereas if you look at the right-hand side of the graph, you can basically see the latencies were very close to each other, less deviations. But if you look at the pure latency overall, it was 85% lower in staggered runs. So, which means if you're doing concurrent runs, you'll be able to basically, it'll take much longer to download chunks versus if you're doing one at a time. And this would definitely result, as to highlighted, where device completing the downloads faster and consuming less battery power, and can basically, not interfere with other functions of device, so it can basically, transmit the required data. Now, moving on to the next measurement, which is the average download latency per device. So we wanted to look at a device level, because we have 24 data points, what is the average download latency? And this is basically for the complete package, which is 200 KB in this case. So each device going through 20 iterations of 10 KB each, and basically downloading full 200 KB. And if you look at this here, the package download for staggered run was 78% faster. I think that is significant. And it basically, again, reflects the same thing. Try to complete the downloads faster so that our device as a unit is basically available to the next set of processing and saving battery power. And if you look at the third, which basically is similar in the measurement, but also another way to look at is throughput. A device basically in staggered run basically had 21% higher throughput, which of course resulted in faster downloads, which means there is less contention, for the resources. And these resources could be your base station and tower. In our case, basically the server definitely was running just one content, hosting one content, so that was definitely not the contention. The next measurement is a TCP transmission. So now what wanted to find out why it was taking longer in case of concurrent runs as compared to staggered runs. And this is one important matrix. TCP transmission, and in any TCP transmission, there is always some retransmission, especially if you are basically downloading or accessing content over a wireless network, wireless channel. Some losses is expected, some delays expected. But I think if you look at these two runs, content with staggered runs, the average packet loss was 167% more in content runs. I mean, this is a lot. I mean, for a comparable test running on the same device, again, the same network, with all the parameters remaining same, this is significant. And this matrix, as we're seeing, is per device. We want to see like per device, right? And what we want to do next is basically to see if there is an aspect of time in these packet loss. Is it basically higher at certain point of time? And that basically led us to kind of look at the next matrix, which basically is TCP transmission across devices over time. So this, if you can see the details on these two graphs, there are peaks, and these peaks basically happen to be around 5 p.m. on weekday. Okay, so on work day. Now this is interesting. I mean, this is why would basically peak at 5 p.m. on a weekday, and I mean, literally we just looked out the window, and this is what we saw. Is this. So this is the location. So this is where our office is, and this is the view outside the office. And we are very close to the airport, right next to the airport. And there's a flyover here, which basically has a meter on light. And around this peak commute time, all these cars basically line up. And I think this would basically, create resource, contention on the base station, which is very, which is serving these devices that we are running test on. And I think it's pretty obvious who wins in this case. The consumer devices are winning, and basically causing these more packet loss for the devices that are under test, and leading to reduced throughput and increased time. And this is, again, this is considered both. This is not like staggered versus concurrent. So this was very fascinating. I mean, this was we kind of predicted this, this contention, and but I think seeing this in real, I think was really interesting for us as an observation. So the next set of statistics or the matrix that we looked at was essentially the RF statistics, basically the signal statistics. And these are something that we basically captured on the device, as I mentioned. So the three statistics that we basically captured, we looked at the SINR, which is signal to interference and noise ratio, which basically indicates the quality of the signal. And the second was RSRP, which is reference signal receive power. And the third one basically was RSRQ, which I'll talk about in a few seconds. So the SINR is basically, which means it's in a good range. The device is not, far away from it, from the base station. And you can see it was really consistent in both concurrent and in our staggered runs. But what is interesting is that, around certain hours between like 2 a.m. to 4 a.m. On all days, the SINR was very good. Okay, it was really a peak. And during this time, if we correlate with other measurements, the throughput and latencies there and packet loss was minimal, throughput was highest, and this was interesting observation. And I think what we believe, it may be like this is the time with the least contention, and maybe the resource allocation for CAT-M is kind of best on the operator's network for this operator one which we used. And I think this was something we'd basically further run and establish, and even discuss with the operator to understand this behavior. The second next RF matrix that we basically captured was RSRP. This basically tells the signal the strength, basically how's the signal from the base station, And this basically, again, was good, consistently good, which basically indicates there's no issue with basically, with the base station here in terms of the coverage. The device was in good coverage throughout. This is good. But the other interesting, the second one, which of like Aeris RP and Aeris RQ, both of these parameters are basically used by the devices, the modems, to evaluate, decisions on whether to switch cells or not, right? Now, while Aeris RP was good, and generally if Aeris RP is good, Aeris RQ what determines, when to basically switch the base stations. So in case of Aeris RQ, if you look at this was mostly good, but it was bad during peak hours, in morning, especially evening. Now this correlates with the commute time, that I basically showed in the previous results, and this basically caused the device to switch cells. And as it's switching cells, doing cell selection, consuming battery, interrupting OTA downloads, and that basically is leading up to the increased latencies and reduced throughput. And what we noticed is that, this device is sitting in lab, it's a fixed device, but it is switching cells, and it basically switched up to 6 to 7 different cell IDs, which is unusual if you basically look at where we are, where the devices are located. And then we wanted to also look at whether this cell switching is happening, what is the time correlation with this cell switching. And if you look at this also correlates, with the Aeris RQ measurements, that the device is switching cells, and it is switching cells most around those peak commute hours. And if when we looked at, the cells where it is basically, positions, those cell towers, this is the location of cell towers as I'm showing it on the screen. Is you can see on the right hand side, on the map, there's a blue dot. This basically is the location of the lab or office. And right next to it, there's the cell tower, the base station here. This should be the best tower for this one. But if you see, during these peak hours, it is basically switching, and it is jumping between the two at the airport, and there's one at least 1.5 miles away from the location, right? So this basically, again, is a resource contention on the base station, which is basically closest to our office, because, a lot of incoming flights around the time, there's people's peak commute time, causing it to basically, switch cell selections. So essentially, so this basically wraps up the set of results that we captured. At a high level, if I basically just summarize before I hand it over to Drew to conclude, is the concurrent and staggered runs. Basically, one is a resource competition with the consumer devices, non-LTE-M devices. That's one, and the second is basically if you basically use the knowledge of connectivity, then we basically see a drastically different performance measurements in the two runs, concurrent and staggered runs. So I think now I will hand over to Drew to conclude, share the conclusions.
Okay, thank you, Naren. Those are really interesting data points relative to this testing. It's really, really very interesting. So, and just to re-summarize what we learned out of those results. So we talked about LTE-M. We talked about the advantages and the trade-offs, how those advantages and trade-offs might interact with OTA. We talked about a case study that indicated that there was kind of an interaction, and then we re-showed a lot more details about why there's that interaction in our own lab testing. And what we saw was that if we do unmanaged, unaware OTA campaigns, there can actually be significant degradation in performance. And what we need to do is turn the staggered OTAs into the concurrent OTAs into staggered OTAs that relative to each particular cell tower and base station. That's actually what we need to do. And in order to do that, we can use the cellular network location. That's the important kind of takeaway here. And what we get out of that is if we make our OTA campaigns connectivity aware, and we use the cellular network location, then we can get faster downloads, we can get better throughput, we can get less packet loss. And actually, it was really surprising how much of an impact the packet loss was. And for our customers, packet loss means cost, actually. So fundamentally, you're going to save money if you make your OTA download connectivity aware, and you're going to get improved battery life. And the good news here is that we have existing Aeris APIs to get the network location. You can integrate that into your OTA campaign management in order to make it connectivity aware. And then the other piece of information that came out of our detailed analysis was how much time of day mattered relative to many of those same capabilities. And we are going to take those learnings and figure out how best to get that information in front of our customers so that they can take advantage of that capability as well. So those are really the key takeaways from all of those things that we went through. Thank you again, Naren, for all that great data and analysis. And now I think we're ready for handing it back over to the other Drew, actually, to walk through maybe some questions for the audience and answering some questions from the audience.
Okay, perfect. Thank you both for an incredible presentation. And now we would like to do 2 polls before we conduct our Q&A session. So the first poll that you'll see on your screen now reads, do you currently have an OTA campaign manager? Please respond and submit your answers. Okay, so 8% of you do have an OTA campaign manager, while 92% do not. Drew or Naren, did you have any comments on this?
Well, I'll just say that, again, it's super interesting. And for those who don't have OTA campaign management, it is definitely something to consider adding to your program. And maybe you can talk to us and we can point you in the right direction there.
Perfect. And then the second poll question is, are you currently planning to deploy LTE-M? Okay, 45% of you are not planning to deploy LTE-M, while 55% of you are not.
I'm sorry, Drew, can you restate that? So 45% are planning to deploy LTE-M?
Yes.
55 are not?
Okay. Are not. I apologize for that.
Gotcha. Okay, that's great. Very good. And I think, we'd be interested in maybe, we can't frame that in the context of a poll question, but understanding what other topics similar to this topic that people might like to know more about in the future would be very interesting for Naren and I to understand. Maybe you can find a way to get that information to us.
Yeah, absolutely. Okay, and now we'd like to enter the Q&A portion of the webinar. For starters, does Aeris provide an OTA campaign manager?
Great question, relative especially to the 92% don't have a campaign manager. The answer to that is in our Aeris Mobility Suite that we talked about in the very beginning, we do have a campaign management capability that's specifically for moving things. We do not have a generally available OTA campaign manager for all of our connectivity customers. But it's interesting. It's something that we've talked about internally and may consider in the future.
Perfect. Thank you. Another question that we've received is, how much does an LTE-M radio module cost?
What we are seeing in the market, and of course we don't sell radio modules, but what we see in the market is that at volume, LTE-M radio modules can be well under $10, and that's what's making them very attractive to many IoT programs. That this is really, an important inflection point for a bunch of existing IoT programs and new IoT programs that can get their total BOM cost down to a level that delivers the ROI for their use case.
Perfect. We have 3 more questions so far. First being, are there particular networks where the congestion is more severe than others?
Yeah, I don't, Naren, maybe you can give an answer,
Yeah.
try to give an answer there, and then.
I think, we basically, in this case, we did this experiment on one network. It's a well-known tier 1 operator. But I think maybe I think Drew can add that we have some data point from other operators in terms of, how they basically allocate, the source blocks for CAT-M services. And that basically, varies, so there's no standard. And so I think it's very likely we'll basically see different, performance variations between different operators for sure. But I think we would definitely like to basically, run these tests and confirm, so that we can provide guidance to the customers as well.
Yeah, excellent point. And I totally agree with Naren. Firstly, I think all of the operators are starting with pretty constrained, limited number of PRBs, of resource blocks. And so you'll see constraint. You might see some variation over time where, some operators allocate a little bit differently. And then, but again, if you kind of think about it from their perspective, that's going to be demand driven. And they're unlikely to really, they're not going to be optimizing for the OTA use case. They'll be optimizing for the standard LTE-M use case primarily.
I think maybe if I can also add, though it's not part of the question, but I think it's still interesting, is that I think we're also looking at, it's the one is the transport, the other is the protocol, right? The protocols can also play a significant role in basically taking advantage or working around really these constrained networks. And so that's another aspect that we're looking at, as part of our labs activity to run these tests and come with a recommendation, like what protocol would be best, basically. TCP is not the best in all the times. So, there are a lot of other protocols, that can be leveraged to basically, work around these performance differences and things like that.
Good point.
Okay, thank you. Another question that we've received is, at what scale would we need to consider automation, which is aware of the underlying network / connectivity?
Yeah, I mean, I think you saw even in our lab results and also in the case study that we talked about, it actually is at a relatively small number. So anytime you get a relatively small number, I mean, even in the single-digit number of devices on a single tower, you can run into this type of situation. So if you got a factory or distribution center, or even in the field where you have a cluster of devices, then you're going to benefit from making your OTA be connectivity aware.
Okay, and the final question for the two of you is the congestion problem expected to be worse in NB IoT?
I think it would be because the protocol and the device is more constrained. The bandwidth and the channel allocation from the operators is further constrained. And I think it's the class of application where NB-IoT is basically is for. I think you would definitely see more constraint and need to better manage it. And I say, like, not just play with the locality of the device, but we also need to play with either encoding and the various protocols. So I think that there would basically be more specialized protocols for, NB-IT kind of devices. If payload is small, and how they basically efficiently download it. So true.
It's actually, it's a great, really good point, and it's part of the reason why, we're seeing NB-IT a bit behind where LTE-M is. That, for our customers, we think it's mostly too early to for many use cases, for most use cases at least, to deploy in mass on Cat-NB. We think it's coming, but it's not there yet. And some of the things that need to get resolved are items like OTA and how that's managed in the world of NB. So there's definitely the problem is likely worse or more acute and needs more work there.
Thank you. And with that, I would like to thank both Drew and Naren for a great presentation. I would also like to thank Aeris for providing the audience with a great webinar. Lastly, thank you to everyone who attended today. We hope you learned something new that will help you in your developer career. Have a great day.